Hey everybody, so this is the first lecture dealing with the second section of thermodynamics. So what we're going to do, as I said before, this is a completely different concept compared to what we talked about before. So starting off, I just want to quickly do a little like mini lecture about temperature. So one thing is, as you know, temperature is something that we use to kind of describe how hot or how cold it is. However, uh, temperature is actually specifically designed as the average amount of kinetic energy that each particle has. Now, don't confuse this with something like heat. Now, heat and temperature are related, but heat is about how much energy flows between two systems that have a temperature difference. All right, so one is a flow of energy, the other one is an description of how much current energy the object has. All right. Now, even though we call it and say that it's the average kinetic energy of each particle, it's not actually a type of energy. So don't think of that either. Temperature is not a type of energy. It's just related to the average kinetic energy of each particle. All right. So there's a bunch of different temperature scales that exist. Each one has its own purpose, and each one comes from a different thing. So the three main ones that we're mainly going to focus on are the Kelvin scale and the Celsius scale. First, those are the two main ones that we're dealing with, but you may see some temperature in the Fahrenheit scale, so you might have to actually convert that into Celsius and Kelvin in order to do the math. So these three are the main ones that you would see, usually dealing with Kelvin and Celsius though. Now, whenever we talk about the thermodynamics of this, there's a thing about it that you have to recognize is that we tend to have to talk about what's going on at the microscopic level and then how that affects what's going on at the macroscopic level. So that's a big thing with thermodynamics that we have to discuss what's going on at the little tiny atomic level and then how that's affecting everything in our perspective. So things like temperature, how is that being affected? How is that working on the microscopic level? And then what's that doing with things like pressure and heat and all this stuff? So this is something that you're going to want to have to kind of try to think about is how it's working at the small level and on the big level. All right. One thing that we're going to be using is this. So because we're looking at the microscopic level, that means the masses that we're doing are going to be really, really small. If you don't remember, the mass of a proton is 1.67 times 10 to the negative 27 kilograms. It's an extremely small number. So if we're doing things at the atomic level, which is only a few protons here or there, we tend not to want to do that. So instead, we use the unit of unified mass unit, or AMUs. This is not a standard unit, meaning any equation that we're going to give you, you want to make sure that you might be given numbers in AMUs. You're going to have to convert them into kilograms later on. Now, the way we find, or the way we defined the AMU is that we take the mass of carbon 12 and we divide it by 12. So we take a carbon 12 atom and divide it by 12. What this actually does is it's pretty much taking the average of all the protons and neutrons in it. So one AMU is about 1.66 times 10 to the negative 27 kilograms. So again, it's a roughly about the same mass as a proton. All right, so just quickly doing this. So let's estimate the average distance between the centers of neighboring copper atoms. So we're going to use the density of copper and the mass of copper in AMUs. All right, so pause the video, work on this stuff, and we'll go over it in a second. All right, so based off of this, well, they give us density and they give us mass. The only thing that I could think of that relates the two is the density equation, mass divided by volume. So let's actually just start with that. We're going to have to take this AMUs and convert it into kilograms, since this is measured in kilograms. And then I have to, let's just find the volume. So I get that the volume is that it's this meters cubed per atom. So this is how much volume each atom is going to take up. Now, first, they want us to estimate the average distance, meaning we just want to kind of get a rough idea of where it is. So the thing is that volume is proportional to the radius cubed. So I could always just do like, oh, it's probably separated by a sphere around it and find the actual radius. But again, I'm estimating. So I'm not going to worry about what constants are in front of the r. All I care about is that there's this direct relationship. So what I can do is I could roughly estimate that r is going to be the cube root of this volume, which gives me this distance. So 2.28 times 10 to the negative 10 meters per atom. So that's the roughly the distance between neighboring copper atoms. All right. So thermometers, as you know, are used to measure temperatures. Now, the way we actually set up a thermometer is we need 2 points, typically in order to get the scale. So usually these temperature scales, the 2 points that they use are based off of some sort of phenomena as a reference. So for example, for Celsius, the 2 points are when water freezes and when water boils. And then they set that equal to 0 degrees Celsius for when it freezes and 100 for when it boils, and then they just divvy up everything in between evenly. So that's how the Celsius scale comes from. Now, the Fahrenheit scale is a little bit different. Actually, I'll just go through them in order. So Kelvin's pretty easy. It takes the Celsius scale and it relates it to absolute zero. So as you know, we found that there is a lowest possible temperature that any object can reach, and it was found to be negative 273 Celsius. So what they do is they just take the Celsius scale and just move it down so that zero is now absolute zero, the coldest possible temperature. So for the most part, it's just a shift in the numbers, nothing too much. This is going to make a lot of our calculations a lot easier later on, as I'll mention. Now the Fahrenheit scale, a little anecdotal story that I was told was that the Fahrenheit scale was determined when a scientist went outside on a very cold day and he went, ooh, this is a cold day, coldest day it's ever been. I'm going to call this zero on the temperature scale. And then he went inside and his wife had a fever and he puts his hand on her head and says, ooh, honey, you're hot. You're the hottest it's ever been. I'm going to make that 100. And then he used that as a scale. Now, that ended up not actually being accurate. The way it actually turns out was that he did something similar to what Celsius did, where he took the lowest the freezing point of a liquid and the boiling point of a liquid, but instead of doing straight up water, he did salt water or brine water. So it kind of has a little bit higher and lower melting and freezing points. And also, he did a weird thing where he had it divisible by, I think, 13 or something, some weird number. I think some sort of Illuminati thing, Masonry thing. I can't really remember the exact number, but it came from that. So that's why the Fahrenheit scale is a little bit weird, but it is based similar to how Celsius was. Now, there's one scale that you probably never heard of is the Rankine scale. Now, the Rankine scale is essentially the Kelvin scale for Fahrenheit. So it does the same thing. It takes the Fahrenheit scale, shifts it over so that 0 Fahrenheit, zero Rankine is absolute zero on the Fahrenheit scale. Then there's this Romer scale, a Noonan scale, the Delisle scale, the Reaumur scale. Basically, all these are done the same way. They take 2 points, some sort of, like I said, based off some sort of phenomena, and they determine what those numbers are going to be, and then divvy up based off of that. Um, so yeah, here is that. Oh, that's spelling error. That should be brine. Um, so yeah, here's kind of how the temperature scales are done. Now there is here this one, the Planck scale. This one I actually like the most. So the Planck scale takes the concept of the Kelvin scale and extrapolates it even more. See, it turns out that we actually also know that there is a highest temperature that a substance can reach, and that's considered basically absolute heat or absolute hot. So what the Planck scale is it takes absolute zero and sets it to zero, and it takes absolute hot and sets it to one. So essentially, any possible temperature is somewhere between zero and one. There's nothing above and nothing below this scale reading, which I kind of like a lot. So, for example, 0 degrees Celsius would be 273 Kelvin, which would then be 1.93 times 10 to the negative 30 on the Planck temperature. So, something I like. Now, we're going to end up talking about the laws of thermodynamics. We have to start with the zeroth law of thermodynamics. If you've ever learned about like different types of laws in either math or science, you'll know that every now and then they end up having to throw in a zeroth law. Typically, what this is that usually laws were developed. You know, there was a first law, a second law, third law, but in order, but one of the things they kind of overlooked is something that they didn't realize that they had to say, so they come up with a zeroth law as a way of saying like this is something that needs to be said, but for the most part there's really nothing crazy about it. So for example, here the zeroth law is saying that if two systems are in equilibrium with a third system, then they're in equilibrium with each other. So for the most part, that's something that everyone pretty much knows, but it's something that has to be said in order for proofs later on to work out. It basically is kind of like the idea of saying like, oh, if A equals B and B equals C, then A equals C. You know, that idea that if two are in equilibrium with one, then they're in equilibrium with each other. Now, temperature is what we actually use to determine whether two systems are in thermal equilibrium. Typically, the main idea being that if their temperatures are the same, then they're in thermal equilibrium. So that's usually whenever you see the word thermal equilibrium, just think that their temperatures are the same. And when they're the same, there's no net transfer of heat. So when you have two systems that are in thermal equilibrium, it doesn't mean that there's no heat being transferred to each other. It just means that the amount transferred from one system to another is equal to the amount of energy transferred from that system back to the first one. So, you know, if 5 joules of heat are transferred one way, 5 joules of heat is transferred the other way as well. So that's why we say it's no net thermal exchange. All right, so again, that was a lot of the basic stuff. We're going to talk about thermal expansion in this first video, and then in the next video we'll talk about the ideal gas law. Both these are fairly big stuff. So as you know, when items are either heated or cooled, they'll expand and contract accordingly. It's one of the reasons why putting things in the freezer sometimes causes it to explode because of the expansion of it, or why when you go to close your door in the summer, you may notice it's sticking a lot along the edges along the frame, but then during the winter you can close it easily. or why when you're building something in the winter time, you really need to make sure that there is a gap between wooden planks for that expansion. Now there are, for the most part, every item expands and contracts pretty much in a similar way. However, things like silicon, water, gallium, all these items tend to disobey this idea over small temperature ranges. What I mean by that is instead of expanding when they're heated, they'll expand when they're cooled. So they kind of do that stuff. Now there are some materials that actually disobey all the time, meaning when they heat, they don't necessarily expand; they may contract, and vice versa. So this kind of shows the density of ice. So here, when the temperature is in the above zero and it's in its water phase, you can see its temperature is sorry, not temperature. Its density is constantly increasing, which makes sense as it's being cooled because it's contracting, it's getting more and more dense, it's getting to that solid phase. But then once it becomes ice, it pretty much drops dramatically and ends up having a smaller density compared to its water phase right before, and then it will start to increase again. This is one of the reasons why water ends up floating, and that is actually one of the reasons why water is one of the most important uh, materials that we're looking for when it comes to searching for life in the universe. I think I'll mention this again later on. All right, so the expansion. So remember how I said that one of the things that we have to worry about is this whole idea about what's going on at the microscopic level and how that affects at the macroscopic level? Well, the whole idea is that the expansion of the material, the macroscopic, is actually caused by the intermolecular molecules and the distance increasing between them. Basically, the idea is that when you increase the temperature, the molecules will start to move around more. And because they're moving around more, they'll now kind of start spreading out between each other. So the distance between the molecules will start to increase. And because the molecule distance is increasing, well, that's going to cause the material actual macroscopic length to also increase. So the amount that the material can actually increase is based off its coefficient of linear expansion. So this is based off of the material and is temperature dependent. So the symbol that we're using for coefficient of linear expansion is an alpha. And the units are either going to be inverse Celsius or inverse Kelvin. Now you'll see why I'm mentioning this in a second. All right. So the equation is delta L equals alpha L naught delta T. So you have some sort of initial setup. Usually what they do is they'll tell you its initial temperature, its initial length, and then it'll tell you a new temperature, and then you're going to have to figure out how much it expands by, or vice versa. Now, going back to this, why is it that alpha can be inverse Celsius or inverse Kelvin? Well, it's because of this. So I said before that it's kind of nice sometimes that the Kelvin scale is the Celsius scale just shifted over 273 degrees. The reason why I said that's nice is because whenever you see an equation that's delta T, you can use either Celsius or Kelvin. Either one works because the numbers are separated. They're using the same scale, so they're separated by the same amount. So for example, the difference between boiling and freezing for water is 100 degrees on the Celsius scale, but it's also 100 degrees on the Kelvin scale. So that ends up working out either way, so you can do that for both. And this is something that's true for any equation that you're going to see in this section. Whenever you see delta T, you can use either Celsius or you can use Kelvin. However, Once you see temperature by itself, so just straight up T, normally in this class you're going to need to make sure that you convert that to Kelvin. Now we can actually rework this, separate the delta L into an L minus L naught, and rewrite it so it looks something like this. So again, two sides of the same coin. Choose the one that's being set up for whatever you're looking for. You're looking for the final length. This is what you'd want to use. If you want to find the change in temperature or the change in the length, this would be the one you use. All right. Now, when you're dealing with volumes, what you would want to use instead is the coefficient of volume expansion, represented by a beta. It's also sometimes called the compressibility. Now, the numbers are on here on this table. So again, it's in your textbook. But any test I give you, I'll give you these numbers if I'm having you do something with this. So you can see the linear expansion values and the volume expansion values. Now, the equation ends up being pretty much the same thing, just replacing the linear lengths with the volume. But it turns out if you actually look at these numbers, there seems to be a weird relation that if you notice, the volume expansion constant is about 3 times the linear expansion. Like if you take aluminum, 25 to 75 is a factor of 3. 56 to 19 is 2.9 or close to a factor of 3. We could do that for all of these and see that, for lead, this is a factor of 3. So a lot of these are off by a factor of 3. We're actually going to show this proof in a second. All right. So before we do that, here's the first video. You can pause it, work on this yourself, and we'll go over in a second. All right. So what we want to do is we want to figure out how much does it contract and how much does it expand. So what we're going to do is we're going to figure out how much it contracts going from 20 to negative 30, and then how much it expands going from 20 to 40. So we're just doing the equation twice. So first, to figure out how much it expands by, we plug the numbers in and we get about 4.8 centimeters. To contract, we use, again, the negative 30 this time, and we get negative 12 centimeters. And if we want the total difference, we're going to add these two, and we get that in total it's going to expand and contract about almost 17 centimeters. So from its longest point to its shortest length, there's about 17 centimeters of difference. All right. Now, a good example is the Golden Gate Bridge, which is extremely long, will end up expanding about 65 centimeters during the summer. Now, the way that we fix this with bridges, because that would, if we think back to the first topic, increasing the length of a bridge, but forcing it to maintain its length, will end up resulting in increased amounts of tension or compression added onto the system. And too much of that will end up causing it to fracture. So what they do, if you actually pay attention to bridges, they tend to have these little expansion joints. They look something like this, where they have almost integrated teeth into each other, like this. Yeah, my amazing drawing skills. Yeah, so you'll see that they have these interlocking teeth that look almost like a zipper, and you'll notice that there will be times where there's actually a gap between them and where they're actually getting closer together, and this is what's actually being used to kind of help with the whole expansion and contraction. Something similar also gets used with the concrete slabs and sidewalks. If you'll notice that there's pretty much always like a little gap between things. Typically it's for the same idea that when during the heat, when the concrete slab expands, you don't want the concrete to be butt up against each other and increasing some added compression that's not necessary. So they put these little gaps in between them to make sure that there's not it can expand and contract at will. All right. So here's another one. What So read the question, pause it, and work on this yourself, and we'll go over it in a second. All right. So the whole idea is that we want to try and get a ring to expand large enough so that a rod can fit inside it. The ring is initially a little bit smaller than the rod uh, when they're at the same temperature. So we're going to have to try to figure out what temperature this needs to be at to expand enough. And then it also says that we want the diameter to be larger by this amount of centimeters, 0.008 centimeters. So we don't want it to be equal to the rod. We want it to be a little bit bigger than the rod. All right. So we're going to use our same equation. We're going to figure out how much the temperature is going to change by. So what I'm going to do is first I need to figure out, well, how much does this need to expand by? It needs to go from 6.42 centimeters to the 6.445 centimeters. And then it's got to add an additional 0.008 centimeters. So I'm going to take the difference of the two diameters and then add the new one, the how much it has to be bigger by. And I plug the rest of the numbers in, I get that the difference in the temperature needs to be 430 degrees Celsius. Since it's starting at 20 degrees, we know that the ring will end up having to be heated to about 450 degrees Celsius in order for this to work. All right. This is pretty much the concept. If you've ever tried this, where you have to try and open up something, what you can do if it's too tight, you can put the jar's lid underneath the hot water and basically heat it up. And what that'll do is it will cause the jar lid to expand a bit, and then you'll be able to open it up. Now, one thing I do want to point out, because I have tried this at home, first you need to make sure that it is extremely hot, pretty much the highest that is. You'll see this person holding gloves. Yeah, it's going to be pretty much hot enough where you probably would want to wear gloves. And another thing is you probably would want something to actually maintain the grip. I remember doing this and my hand kept sliding because I couldn't grab onto the wet metal. So you might want to actually, you know, use some sort of rubber gripper. It's also actually one of the reasons why if you hard boil an egg and you run it under cold water, it becomes easier to peel. Not only is it stopping it from cooking, but it's also causing the egg inside to kind of compress a bit so that the eggshell is pulled away from it and will be easier to kind of take off. Now, a quick side question is, why would we not want to put a hot jar in the fridge and then open it up later? So try to think about this. And basically the idea is the reverse. So if you put a hot jar in the fridge, then the lid is going to be on very tightly, and there's also going to be a little bit of a, not so much of, I don't want to say a vacuum, but there's not going to be a whole lot of air inside it either, as we'll talk about in the next topic with the ideal gas law. But you end up having a combination of the lid on much tighter because it's much bigger, and the lack of air. So when it cools, the lid is going to tighten up a lot more on that on the jar, and then you also have the air, which now compresses more. That's going to create more like a vacuum seal. So yeah, typically, even if it's not a jar like a Tupperware, you want to try and make sure that it gets to some sort of close to room temperature before you put a lid on it. Because if you put a lid on right away, put it right in the fridge, it's going to be a pain to open up later on. All right. So as I mentioned, want to actually see how the volume expansion and the linear expansion are related. So here, what we can say is, well, let's say this is the equation for the volume for of an object. So this was the volume expansion, and we know that the volume of the object is its initial length, its initial width, and its initial height. So what I can do is say, well, the new volume it's going to reach is going to be equal to the linear expansion of all three sides: the um, the length, the expansion of the width, and the expansion of the height. Uh, so what I can do is actually pull this out and cube it, and then when I take the difference, which is just the new volume minus the original volume, I'll end up getting v naught 1 plus this to the cubed minus v naught. And then this pretty much expands to be roughly equal to this term. Now, because alpha and delta t are both usually really small, and in particular alpha is an extremely small number, when we square it and when we cube it, these numbers are going to be also extremely small. This is actually going back to the whole small approximation. I don't want to call it small angle approximation, but the small x approximation, that when you have a number that's really small and then you raise it to some power, it gets so small you can kind of ignore it. So this basically means that this will actually simplify to being this. Delta V is roughly equal to 3 alpha V naught delta T. So we can see that beta is about approximately equal to 3 alpha. So as I said before, this is kind of where that relationship's coming from, and why all the beta terms seem to be about 3 times the value of their alpha terms. All right. So here's a question dealing with the volume. You can pause the video, work on this yourself, and we'll go over it in a second. All right. So what we want to figure out is how much each one is going to expand going from 20 to 40. So the first one, the gas, when it's going from 20 to 40, will end up expanding about 1.3 liters. Now the tank is made up of a different material, and we could see that it only expands about 0.05 liters. We could tell because of these numbers, the gas is going to expand a lot more than the tank. So that means that the difference in these volumes is going to result in this gas being the excess gas spilling out. So when you do this, of the 70 liters that you filled in, about a little bit over 1 liter is going to end up spilling out of it. So sometimes you're going to want to pay attention and make sure that you actually fill your car up at the right time. Typically when it's hotter rather than when it's colder. Thought I was going to say something else, but I guess not. All right. So as I said before, water is a little weird. The whole thing about ice floating. Typically, um, as ice is heated from 0 degrees, it's going to contract. Like it ends up disobeying the whole laws of thermal expansion between these small ranges. Um, and this is one of the reasons why ice will end up floating. Um, and I said before that this is a critical factor of life. What I mean by that is, for the most part, because ice floats, what this means is when you have a large body of water, the top of the water will actually become ice, but everything underneath will still stay liquid. And in fact, the ice on top will actually insulate the water underneath, keeping it a little bit warm. So that's one of the reasons why we're always so fascinated with planets that have liquid water, and why we always consider it as a place to harbor life is mainly because it allows for a nice ecosystem that when it gets cold, the water will still, at least it won't like completely freeze over. Like if this was the other way around, where ice, because of its density, actually sunk, then any water, body of water, would actually completely freeze during the summer. Now, some other things about water that you didn't know, that you may not know, is one of the other things about water is that it has a very high specific heat, which means that water doesn't like to change its temperature too easily. So it requires a lot of energy for it to change its temperature from one point to another. This is why if you go into the water during the day and then you go into the water at night, for the most part, there's really not going to be much of a difference in the temperature of the water, even though the outside temperature probably went from, 90 degrees in the day to 60 degrees at night, depending on where you are. The water temperature doesn't change that much. Again, it ends up resulting in water having a very nice, balanced, and stable ecosystem. These two graphs are basically showing the whole idea that instead of it uh, increasing like normal, it kind of does like a weird curve between 4 and 0 degrees. All right, so we talked about, I kind of mentioned it before about, the added stress onto a system caused by the thermal expansion. So we're just going to combine them. So if you remember, this was the equation that we had for the change in the length of a system, based off of its Young's modulus and this whole stress term. We can set that equal to the linear expansion equation. The L naughts drop out. So thermal stress, which is F over A, can be found by using this equation. All right. So pause the video, work on this yourself, and we'll go over it in a second. All right. So here we have this question where we're going to try to figure out how much stress is added as the temperature goes from 10 to 40, and want to know if it fractures. So for now, we're just going to use these numbers. We use the thermal stress equation, just do a straight up plug and chug, and we get that the thermal stress on the concrete block is 7.2 times 10 to the 6 newtons per meter squared. Now the ultimate compression strength of concrete is 20 times 10 to the 6. So this it is fairly close, much closer than we would probably want. Basically, any mistake in maybe the length being a little bit bigger, or the temperature being a little bit higher, will actually cause this to get much closer and actually break. Uh, but the thing is, this actually does end up exceeding the tensile and the shear strength of concrete. So, yeah, this is a lot higher than we'd probably want in real life. All right, so I'm going to leave the video at that. And then the next video, as I said, we'll talk about the ideal gas law. All right, so if you have any questions, please let me know. Otherwise, I'll see y'all later.